Welcome back. With the theory of simply supported beams for various loadings now concluded, we shall solve a problem for shear force and bending moment in this lecture. As usual, we draw a schematic diagram of a simply supported beam with a pinned support at the left end and a roller support at some distance inwards from the right end. Let's label the left end as A, the roller support as B, and the right end as C. Let's drop the projections and denote the length AB as 3 meters and length BC as 1 meter. Let's show a uniformly distributed load of value 4.5 kilonewtons per meter acting over the entire length of the beam. The unknown reactions RA and RB are shown in upward direction acting at the supports at A and B respectively. To find the reactions, we consider the entire beam in static equilibrium. The first equation considers the balance of forces in vertical y direction, which gives Ra plus Rb equals 18 kilonewtons. Let's name this equation as 1 for later reference. The second equation considers the balance of moments, say about the end A, for which Rb is found as plus 12 kilonewtons, positive sign indicating that the assumed initial upward value of Rb is correct. Using equation 1, Ra is found as plus 6 kilonewtons. We hence retain the upward direction of the assumed initial direction of Ra since the sign obtained is positive. We mark the values of the reactions on the schematic diagram for reference. Before applying the method of sections, we mark an arrow pointing towards the right at end A, which is taken as the reference end from where the distance x of the imaginary cross-section is measured. We now draw the zero datum lines for shear force and bending moment diagrams. For region AB, for which x is greater than or equal to 0 and less than or equal to 3 meters, the shear force at x equals plus 6 minus 4.5 times x, which is linear in terms of variable x. For region BC, for which x is greater than or equal to 3 and less than or equal to 4 meters, the shear force at x equals plus 6 plus 12 minus 4.5 times x, which is also found to be linear in terms of variable x. Using the equation for the region AB, the values are calculated for the sections at A and B respectively as plus 6 kilonewtons and minus 7.5 kilonewtons and are plotted in the shear force diagram. Considering the region BC, the values are calculated as plus 4.5 kilonewtons and 0 kilonewtons respectively for the points B and C and are plotted in the shear force diagram. Let's mark the point where the shear force changes its sign from positive to negative in the region AB as D. To find its location along the beam length, we assign the shear force equation to 0. Simplifying, we get the distance as 1.333 meters from the reference end A. Now the bending moment at x for region AB equals plus 6 times x minus 4.5 times x over 2, and this equals plus 6 times x minus 4.5 times x squared over 2, which is parabolic with respect to the variable x. The double derivative is found to be negative in sign, indicating that the locus curve of the bending moment equation for the region AB is of a maxima type. The bending moment at x for region BC equals plus 6 times x plus 12 times x minus 3 minus 4.5 times x over 2, which is parabolic with respect to the variable x. In this case too, the double derivative is found to be negative in sign, indicating that the locus curve of the bending moment equation for the region BC is of a maxima type. We calculate the bending moment values for the points A and B as 0 kilonewton meter and minus 2.25 kilonewton meter respectively and plot the values in the bending moment diagram at their respective locations. We know from the theory of elementary calculus that the maximum value of bending moment with respect to x is obtained by taking the first derivative and equating it to 0. And the first derivative also happens to be the shear force at D in our case. The maximum bending moment is found as 4 kilonewton meter for the point D in the region AB by setting x equal to 1.333 meters in the bending moment equation. The parabolic curve is hence drawn for the region AB in the bending moment diagram. Also, another parabolic curve of maxima type is drawn for the region BC in the bending moment diagram. We see that the bending moment curve for region AB cuts the zero datum line at the point E, which is called the point of counterflexure or the point of inflection. To get its location along the beam length, we set the bending moment at x equation for region AB equal to 0. The distance of E from end A is hence obtained as 2.667 meters and is shown in the bending moment diagram for reference. In the next lecture, we shall solve another problem for shear force and bending moment for the case of a simply supported beam with a combination of various loads.